Hello everyone, this is revised edition of my previous video, design of rectifier circuit with filter. Since everyone complained about visibility problem, so I am redoing it. Okay, let's begin this. So here we have rectifier circuit with 24 volt AC 50 Hz supply. So the input will be AC. After rectification, we do get the waveform like this. So what is the function of rectifier? The rectifier is a circuit which converts input AC into DC supply. Basically, we need DC signal to be like this. So we don't need this type of waveform. We need this type. So what should we do? That's a question. Simple. We gonna connect a capacitor parallel to it. Capacitance C. So do you think after connection of capacitor we do get waveform like this? Absolutely not. So output of the waveform will be like this. The output waveform will be like this. So to get like this ripple should be very least. This variation should be very least. So engineers, what do is we generally consider ripple voltage to be very less. So what is this ripple voltage? I'll explain you right now. Ripple voltage is nothing but the variation between this point and this point. The difference between these two is called as ripple voltage. And it is represented as delta VR. So you must choose the capacitor in such a way that you must get very least ripple voltage. So how do we do? That is our question. So to get very least ripple voltage, let us only assume early ripple voltage to be very least. So in my design, let me assume my ripple voltage to be around 50 millivolt, which is very least. With this assumption, let us calculate the value of capacitance. Okay? To calculate the value of capacitance, we have an equation C is equals to I divided by 2F delta VR. I is nothing but load current. Delta F is nothing but ripple voltage, which we have assumed to be 50 millivolt. So F is 50 Hertz. Okay. Now let us assume the load current to be 1 amps. Just an assumption for sake of designing. So let's calculate the parameters now. So current, we have load current, that is 1 amps, 1 divided by 2 into supply frequency 50 Hertz into 0.5, 50 millivolt or 0.5, both are same. After that, so finally we end up getting 20,000 microfarad. That is the value of capacitance we have calculated right now. So another parameter we need to consider is voltage rating of the capacitor. Not only the value of capacitance, we need to even calculate the voltage rating of the capacitor. So how to calculate the voltage rating of the capacitor? That's very simple. Let me explain now. We first, to calculate the voltage value of capacitor, we need to find peak voltage rectified peak or rectified voltage here. So how to find the rectified voltage? Simple. This input supply is 24 volt, which is RMS value. To calculate the peak value, we need to multiply by root 2. To convert RMS to peak, we need to multiply by root 2. So let us calculate peak rectified voltage value right now. 24 into root 2. Then the calculation doesn't end here. What should we do? We need to consider the diode drops. So during positive half cycle, these two diodes will conduct. During negative half cycle, these two will conduct. So we need to consider two diode drops. So the diode drop for individual diode drop will be 0.7. Since we are considering two diode drops, we need to subtract by 2 into 0.7. Finally, we end up getting around 32.54 volt. And this is the peak rectified calculated value, 32.54 volt. Here it is a 20,000 microfarad capacitance. Practically, we usually don't get 20,000 microfarad. Instead, what should we do? We need to select the capacitance value which is near to it. The practically available capacitance value which is nearly it is 22,000 microfarad. And this is the capacitance value which we need to choose for selecting the voltage rating of the capacitor. So the voltage we obtained here is 32.54 volt. 32.54 volt. So the voltage rating of the capacitor should be more than this. If you select less than this, the capacitor will burn out. So the practically available voltage value of capacitor is 35 volt. So in design perspective, the final value of capacitance will be 22,000 microfarad, 35 volt capacitor. And this is the capacitance value which we need to connect here, so that we end up getting with least ripple voltage. So almost like this. Now, after all these things, here comes a picture of output voltage. So what will be the output voltage? What will be the output voltage here? Since the output voltage will be varying from this point to this point, what is the value here? Same, 32.5 volt. 32.54 volt. And what is the value here? Since we have assumed the ripple voltage to be 0.5 millivolt, the difference between these two values is 50 millivolt. So we need to multiply this value 32.54 minus 0.5. We'll end up getting 32.04 volt. And this is the value here. The value here is 32.04 volt. So the voltage variation the voltage will be varying from 32.54 to 32.04. So we don't want this variation. You may tell this variation is very least, but some of them won't even entertain this variation also. So to maintain the stability of the output voltage, we are going to connect a Zener diode here. So what would be the rating of the Zener diode? Since the peak voltage value we have peak rectified voltage value we have calculated as 32.5 volt, so the Zener diode rating should be even more than this. So there is 35 volt Zener diode, and this 35 volt rating is reverse breakdown voltage. This is reverse breakdown voltage rating. And if we connect in forward bias direction, the diode will short. Hence we will connect in reverse biased configuration in such a way that cathode should be facing upward. So this is the 35 volt Zener diode we need to consider. So 35 volt Zener diode which is practically available is 1N4751, and this is the rating of the Zener diode which are going to connect here, which has reverse breakdown voltage of 35 volt. If you select the voltage rating to be less than this, the diode will short. Hence we will be selecting more than this value. Okay. So usually one thing you must know. What is it? During the design of rectifier circuit, connection of Zener diode is least preferable. Why? Because in most of the application, like high current application, connection of Zener diode is not permissible. In my design, I just consider the output current to be 1 ampere. Hence, I have connected Zener diode there. Instead of Zener diode, most of them use voltage regulator IC. To get our regulated output voltage. Even Zener diode here does the same function to get the stabilized output. So after connecting the Zener diode, we end up getting stabilized output. But I have connected Zener diode because the output current is just 1 amps. So in most of the application, as I said, voltage regulator IC is used. So it's very simple design. Hope you understood this video. If you like my video, please do share and subscribe for further updates. Thank you.